Okay, everybody. I did see that you were talking in the stream as soon as I refreshed it. Sorry about that. Just going to do one blanket apology for this whole situation so I don't have to apologize so much moment by moment. Yeah, you're right. I could not see the chat before, but of course I could see it as soon as I ended that last stream. So if you have questions, please message them to me on Zoom throughout this, because there are issues with the YouTube chat feature. Come on. All right, thank you, Lillian. Wow, thanks, Fawn. Okay, all right, everyone. Game theory, here we go. Introduction to game theory. Game theory as a science was famously invented, popularized, perfected by John Nash. There's a book by Sylvia Nash. Okay, switched over to some better Wi-Fi. Again, I cannot see the chat, so if you have a question, please email it to me or give it to me on Zoom. Why can I not see the chat? I don't know. It's a bummer. It's a bummer. There we go. All right. Thanks, everyone. Okay, introduction to game theory. There are two kinds of games. And when I say kinds of games, I mean that there are two possible ways to represent human interaction. And that's a very broad definition, I know. But you'll understand it as we continue. So we have these normal form games, and these are the ones that look like this little box here that you can see. This little box is illustrating the famous prisoner's dilemma that we will be getting into, that your book gets into. That's what a normal form game looks like. In a normal form game, players are unable to communicate with one another. Their moves occur simultaneously, so they're both moving at the same time. So picture something like rock, paper, scissors, right? You've got your hands behind your back, or you've got them in a fist, and you do the 1, 2, 3, and then you both reveal rock, paper, or scissors at the exact same time. So you're unable to make decisions based on decisions that another player has already made. Something really important to understand for game theory is that those participating in the game, the players, are essentially able to see this structure just as you or I are, right? They're able to know the possible moves of the other player. They know the utility that they and the other player will get from certain moves. Sorry, it's frozen, Steven. There's nothing I can do. An extensive form game, which is the kind of game that we're going to start with because I think it's easier to solve than the normal form. So we're going to start with extensive. The extensive form game is in this, this setup. We call it a game tree. See how this one below looks sort of like a tree? In this type of game, players are moving one at a time. So now, instead of our typical rock, paper, scissors, where we both throw rock, paper, or scissors at the exact same time, now we have the sort of game where you pick rock, paper, or scissors, and then I respond based on what you've chosen. Obviously, this is a poor way to play rock, paper, scissors, and the second player is going to win every time. So there are specific games that should be illustrated in normal form or in extensive form. We're going to solve these extensive form games using backwards induction. This is just an introduction. I want you to write this down and have it in your brain. And as you learn more about game theory, these things are going to make more sense to you. In a normal form game, players know each other's payoffs and possible moves. In an extensive form game, players know each other's payoffs, the possible moves that can be taken, and the moves that have been taken. Okay. All right. That's a lot. Let's move forward. Let's do a little example. Give your slides a moment to catch up here. I tried to put the stream on ultra low latency so the playback had minimal lag, but YouTube wouldn't let me. Okay, how to solve an extensive form game. We solve these using something called backwards induction. Let's see, I can definitely draw on this. Okay, backwards induction. The moves that player one makes are going to depend on the response that player one knows player two will have. The example I like to use is, do you ask your crush to the prom if you know they're going to say no? Oh, sorry, Benjamin, there's nothing I can do, man. The Wi-Fi here is just so crappy. I really apologize. And I will absolutely have office hours after this, I promise. I will be on Zoom. So that'll be a great way for us to go over this one-on-one if you need, if the slides are too fuzzy for you to see. Okay. Why do we do backwards induction? Do you in your everyday life make decisions based on the decision that you think another person will make? We need to know the decision that the second mover will make before we can know what the first player will do. Do you ask your crush to prom if you know they will say no? Of course you don't. You have already taken player two's moves into account before you make your own move, which is to ask your crush to prom or not. So here's how we do this backwards induction thing. These numbers at the ends, at the branches of these trees, represent player payoffs. The first number in each pair is the payoff for player one, the first mover. So in this case, that's going to be you. So this is the utility that you get if we end up at this part of the game tree. And then the second number here is going to be the utility that your crush gets if we end up on this part of the game tree. And this is the same for every game tree you'll ever see. The first number is the utility that the first mover will get. And the second number is the utility that the second mover will get. You can see that here we've got these big blue nodes with the name of a mover above them. That shows a fork in the road at which this player will have to make a decision. So in this game, the first mover is you, and you have two options. You can ask your crush to prom, or you can do nothing. If you do nothing, you, your utility, And your crush also gets 0 utility. You're not doing anything. You've basically opted out of the game. It's as though this decision to ask the crush to prom never existed. Now, if you do ask your crush to prom, now it's the crush's turn to make a decision. Now we're at this decision node where it's player 2's turn, your crush. Your crush can say yes, in which case you will get a utility of 8 and your crush will get a utility of 8. Or your crush can say no, in which case you have a utility now of -1. You're embarrassed, you're sad. And your crush has a utility of 9. She feels good. She got asked to prom, but she's kind of an introvert. She didn't really want to go, so it's the best of both worlds. Whatever it may be. One important assumption of game theory is that this utility is given in the same way that we were doing those charts, right, with the quantity of a good you've consumed and the total utility you get from those goods. Those things are totally given. That's just a fact in life. We don't question it. We can't affect it. It's just given. Okay. So let's solve this with backwards induction. Let me change the color of my pen here. My headphones have just told me they need to be charged, which is not a good sign. We will press on. Okay, so backwards induction. We're going to start with the second mover's payoff, okay? If the crush is asked to prom, you have already asked your crush to the prom. Does the crush say yes, or does she say no? She's going to say no because her payoff to saying no is 9. Her payoff to saying yes is 8. 9 is greater than 8. So she knows in her brain that if she gets asked to prom, she's going to say no. Okay, that means that this part of the game is dead. We are never going to experience this arm of the game tree because if we get to this point of the game, the crush is now in charge of what direction we go, and the crush is definitely going to go no every time because the payoff of 9 from saying no is greater than the payoff of 8 for saying yes. Okay, so now you have to reevaluate your moves. Now the game has been redrawn. You know the crush is not going to say yes because she gets a greater payoff from saying no. So what do? If you ask her to prom, she says no, and you get a payoff of -1. If you do nothing, you get a payoff of 0. Which of these is greater? Well, 0 is greater than -1. So you will not ask the crush to prom. This part of the game is dead. It's not even going to get to the point where your crush gets to make because you will do nothing. This end point of the game is called the Nash equilibrium, named after our friend John Nash. Nash equilibrium, possible end point of a game, right? Once you've gone through and done your backwards induction, where you end up is your Nash equilibrium. Boom. All right, I'm going to take my headphones off. Guys, please let me know in the chat if you can still hear me, okay?